All right, the doors seem closed, the lights seem on, everyone seems settled. I think that's my cue to go. Also, the clock says 12:59, which is kind of bothering me, so maybe I'll just kind of bide my time for like 20 seconds. Or however many seconds may be on that clock. How about before I actually dig into this talk, I do a little survey of the audience. Who has a right hand? Great. Who has a left hand? Who here is interested in working with large amounts of data that might be in a distributed system? Cool. Who here uses Hadoop? Cool. Yeah. When you use Hadoop and try to do data processing, who here uses MapReduce? Who here uses Spark? Cool. Who here already writes Python? Cool. Yeah. All right. I'm super amped for this talk now. Okay, survey done. Hi, I'm Juliet Hougland. I'm here talking to you today about Sparkling Pandas. Except this is a classic bait and switch that you have walked down into and sat down in. You thought you were buying an Xbox. Really, you were buying a picture of an Xbox. I'm actually really hoping that you thought you bought this really specific talk on Sparkling Pandas, and in reality, you're getting an Xbox. Everyone gets an Xbox. I'm sorry, I don't actually have any Xboxes. I've reframed this talk actually to be what I hope is more interesting. This is a talk about distributed data frames, and Sparkling Pandas, what I was going to talk about previously, is a Python distributed data frame library. But in the sort of time between me submitting this talk and me giving this talk, I realized there's actually like a few that I should talk about to make it more sensible and interesting and show you all the options. And so I'm doing that instead. So here is like your, kind of Xbox, except it's just me on stage for 40 minutes. So I hope you like that as much as video games. So I'm a data scientist at Cloudera. Part of my job is to go talk with customers of Cloudera, see what tools they use, and what sort of things they want to do, and I try to help them do that with huge amounts of data. So a very, very common thing for me to hear is when I go into a customer and ask them, like, hey, what do you do? What tools do you use? What's your world like? Very frequently I'll hear, we do Python. We have scikit-learn for building models. We use stats models to fit statistical models. Under the hood, there's a lot of like SciPy or NumPy. And of course, Pandas is in there somewhere, as well as Jupyter with their notebooks for sort of visual exploration. And a really sort of common core thing that we see over and over again is that the way people want to sort of structure their data and think about their data is in terms of tables. So something you might have an index in, you have named columns. And Pandas in particular has emerged as the default data format for Python data analysis. And so I'd call it a default analytic data structure. Much like a list or a map, having a table with named columns and indices that you can access is so beneficial that it's become ubiquitous and universal. You see it in Python. R has it built into its core library. So data frames are awesome, and they're at the center of everything. Tabular, indexed, you can do data alignment, you can do slicing, you can do filtering. It's good for just sorting your data and having some sort of conceptual model of what it is. So I'd also claim that data frames are central. So R is baked in data frames into its core language, whereas Python, a default data frame has emerged, and that is a Pandas data frame. Under the hood, it uses NumPy arrays, but it's very easy to interact with stats models or scikit-learn in order to use data that you have in a Pandas data frame inside of these libraries. Another good example of this is the Seaborn library, which is, they don't have a cute logo. And so there's a little graph at the bottom there, I represented it. But you can specify the data that you want to plot in Seaborn by just passing it a data frame, giving it column names. And so this is the world that people live in, libraries people use. And then suddenly they're faced with this problem where they suddenly get big data. They had a little pile of data before, and either over time all the datums accumulate and there's just a huge amount of it that's hard to operate on, or you start having access to data sources that you didn't before. So anytime I put the word big data on a slide, I feel like I necessarily have to address what I mean. So what is big data? I don't know, maybe something like that. The way that I would describe and characterize big data is the type of data that is so large that the process of moving your data to where you're going to do your computation is onerous and expensive, and instead you want to move your computation to where you store your data. So we now need to think about, okay, well, the computation that we want to do, or at least the computation we want to describe, is existing in Python. And our data, at least in my world, is going to exist out on some huge Hadoop cluster out there. Well, how do we bring Python to that Hadoop cluster, or at least describe the operations that we want to do on our data in Python? So the previous state of the world, if you had asked me 2 years ago, 3 years ago, I do Python, how do I access a huge amount of data on a Hadoop cluster? I would say, well, you got this big canyon you're going to have to walk across. You've got your data over there and your Python over there. Previously, I think the best option would have been a tool called MRJob, or Mr. Job. It was created by Yelp. And it uses MapReduce, and the mappers and reducers write to standard out and read from standard in and just sort of pipe it to Python processes, which is a thing that worked. But it is maybe challenging to use consistently and easily. And so in the intervening time, things have changed, and it's become significantly easier to use Python with large data sets. So let's think about why this is. Well, I would claim that it's because we now are thinking more about tabular data, which implies relational algebra. You're not excited about the relational algebra? You should get excited. So we have better abstractions that let us actually think about tabular data, right? When we're working with MapReduce, we were operating on key and value pairs, which, yes, over that you could build an abstraction that would work correctly for you to think about tabular data easily, but it is not the most natural thing in the world. So I think our new abstractions are moving more towards tables. And once you have tables, you have relational algebras. And so there's 2 tools that I'll be talking about that are used to actually operate on this. I've already mentioned MapReduce as the sort of predecessor for these tools. And I will then move our sort of execution logic and talk about what sort of execution we do over towards Spark. Who's heard of Spark? Okay, yeah. As well as Impala. So data frame is just another word for nothing left to lose. I mean SQL tables. Just another word for SQL tables. And this is because we have tabular data. We want to do operations on it like slice, project, we want to filter out different columns. Data frame's just another word for I have some SQL that's going to go on underneath the hood. It lets us operate on our tabular data, join 2 different data frames together. But on the surface, it's something that's closer to the sort of APIs that we're familiar with from R and from Python, and significantly more testable than SQL strings. Like query strings are sort of really hard to test, I think. But if you write a Python code, you can actually write a test suite that accompanies it. So when I say data frame, it's really just another word for SQL. But there's kind of 2 parts to this, right? Data frames are mullets. You've got the sort of surface part of a data frame, which is the APIs, the thing in front that you see. Sort of a nice, hopefully smooth API that reminds you of things you're used to working with in R and Pandas. And under the hood, since we have these tables and we have tabular data, and we've started to, this little clue went off, oh, we have tabular data, we can start thinking about relations and relational algebra and SQL. Well, under the hood, maybe all we need to really have distributed data frames is SQL, query execution, in a distributed way. So in order to talk about Ibis and Ibis and Spark data frames and Sparkling Pandas data frames, there's 2 components that we need to be able to talk about. The first is what are the APIs? How are the APIs similar and how are they different? And the second is the execution engines that actually perform the SQL operations that you're describing in the APIs. So I will first talk about API differences, then execution differences. So I claim that in Python, pandas is the default data frame. It is the API that when you think of a data frame in Python, it's probably the one you think of. I actually don't know of other ones. I'm sure they exist. I'm going to use pandas as a baseline for a comparison of these APIs. So let's start with Spark data frames. And this API comparison will maybe make obvious why Hougland, Karau, and I created Sparkling Pandas as an alternative API for Spark data frames. So I usually try not to put too many pictures on slides, or too many words on slides, and so I'm trying to apologize with the puppy picture. I hope you accept it. So the PySpark API is trying to match the Scala API as much as possible, to the extent that it violates PEP8. And it makes my skin crawl to violate PEP8. I don't even know what I'm doing with my life if I'm not following the sort of uniform standards of a language. And so part of the reasoning is that I think the Spark developers are hoping that people that use Python find it easy to transition over to using Scala. I mostly find that I need to disable different PEP8 warnings, which I do not like. So, example is group by versus group by. There's also, beyond the sort of surface differences, Spark data frames exposes a smaller area of the Pandas API, which is not surprising, right? The Pandas API is very, very large. It has plotting functions that integrate with matplotlib. It has all kinds of things that you wouldn't expect early versions of anything to have, right? And so it really only addresses the sort of SQL execution that's underlying data frames. Another aspect of this is that in the methods that exist, the semantic meaning can differ. So let's say you summarize or describe a data frame and you get back information about the columns, you get the mean, you get the standard deviation. In Pandas, you get the unbiased estimator of the standard deviation. In Spark, you get the biased one, divided by n instead of n minus 1. Subtle semantic differences in what is actually going on under the hood. So there are many ways in which I have found the Python API for Spark data frames to be very much wanting. Thus, my friend Hougland and I created Sparkling Pandas. And this is an accurate representation of how the first version of Sparkling Pandas worked. So our goal in this project was to create an API for Spark data frames that matches the Pandas API as close as possible. The way that we did this was that under the hood, we had a bunch of Pandas data frames, and we would use operations from, called on the large distributed data frame and do them on the little data frames and aggregate them in some smart way. And so it really was like tiny little pandas controlling the big pandas. So now compare Python versus Ibis data frames and that API. And the short answer is that it's a lot more Pythonic. Ibis is created by Wes McKinney, who recently started working at Cloudera, the same company I work at, about a year ago. And it's a descriptive language basically for generating SQL. And he's very upfront about this. It's like, this looks like a data frame, acts like a data frame, it interacts really well with Pandas in local scale. And it's just going to generate SQL, which you can sort of output anywhere. So the short version is that it's extremely Pythonic. But it's similarly not as quite broad of an API as Pandas has. An interesting part of this is that there are interactive and non-interactive modes. So if you are running Ibis in a notebook, for example, you can create a data frame that points at a file and say, here are the sequences of operations I want to do. And in interactive mode, it'll immediately execute them. In non-interactive mode, you can tell it to sort of batch up all the sequence of operations that you specified, and then execute them when called. So the API differences are sort of surface, and you can get around them. And I think the more interesting comparison here are what the execution engine differences are. So SQL execution differences. PySpark data frames and similarly Sparkling Panda data frames are built on top of Spark. So Spark is a distributed framework for data manipulation. The way that I think about Spark working is you have what they call an RDD. And a data frame is really, a Spark data frame is really a wrapper around RDDs where you have RDDs of rows. And you describe the operations that you want Spark to do. And you say, okay, first I'm going to get you to read in this text file, then I'm going to filter out these columns, I'm going to join these two RDDs together, and I'm going to write it out to a file. It generates a DAG of those operations, and then when it goes to execute, it executes those as tightly together and smartly as possible, very similar to the non-interactive mode of Ibis. Spark also has a lot of components. So there's Spark Core, which is the orchestrator for the operations I just described, which is defining what sort of operations you want to do on your RDD, and then doing the orchestration of sort of farming that out to your different worker nodes. There's also other parts of this. So there's MLlib, which is really nice, big distributed machine learning library, and Spark SQL, which is actually where data frames live. So data frames came to be, I believe, in Spark 1.4, and it was a renaming of one of the core data structures inside of Spark SQL, unsurprisingly, since data frames are just another word for SQL table, right? And I think part of the reason that the API is not what you expect from Pandas is that it was originally built very much in a SQL-oriented way without thinking about what the higher-level data frame APIs people are used to are really like. So, PySpark data frames. There's a few advantages and disadvantages to each of these. And in particular, I think Python has a lot of overhead in Spark, and I'm going to talk about those issues a little bit later. So the Python language, Python data frames are the Python language interface for Spark. If you're going to use PySpark at all, it's highly recommended that you do as much of your operations inside of data frames, as many of your operations inside of data frames as possible. So there's a few really nice things about this. With PySpark and PySpark data frames, first of all, Spark itself in its core is written in Scala, but you don't have to write Scala. So that's nice. This doesn't mean you actually don't have to understand Scala a little bit, because you're still going to get Scala exceptions. I know, I'm sorry. And the real benefit that I see to PySpark right now, that is just huge, is that it supports UDFs, meaning user-defined functions. So you can say, hey, I have this Python function. I want to apply to every record in my data set that's distributed on a cluster. And it will actually take that Python function, ship it off to the cluster, and apply it for you. This is a non-trivial amount of work. It's very tricky, and not a lot of systems actually allow this yet. The cons to this is that, and I've actually seen fast in the pros, so it kind of depends on what your version of fast or slow is. But I think this is kind of slow. So if you're going to be doing data frame-like operations, and you're going to be doing this with Python, the more interop that you have between Python and the JVM, meaning the more UDFs you have, the slower it's going to be. But if you stick to just doing SQL operations, it can be relatively fast. Another con that I found is that it's not Pythonic. This is the thing that really got me, right? Like, it doesn't follow Pepe. It just doesn't fit together in a way that a Python user expects it to fit together. And one of the cons that is actually associated with the pro of supporting UDFs is that, okay, well, you have this Python function that you defined on your sort of like driver node, your sort of like operations central, and then you go and you ship this function off. And Python, you don't have jars. Like, one of the things in Java that's beautiful is that you can package up all of your dependencies into this big wall and ship it off wherever you need it, and you have the code right there that you need to depend on. In Python, you'll have a statement at the beginning of the function that's like, oh, I need to import this package. And so wherever it's being executed, like, where's my package? Where's my package? Is it there? Is it there? Like, it's very, very possible that out on your cluster you don't have the right dependencies installed. And so while it's a very big pro that you can execute UDFs on a cluster, it's still very challenging to actually manage your dependencies. Sparkling Pandas. As you notice, these are very, can I go back? Yeah, these are very similar slides. The only difference is that Sparkling Pandas is Pythonic. It has tried to match the Pandas API as closely as possible. Our goal is that you change an import statement from Pandas to Sparkling Pandas, and you change the point at which you create your Spark data frames. You actually have some of the other objects that you need to generally use Spark. And then all of your code should still mostly work. This is the goal. So same pros and cons. One thing just got changed where this is a lot more Pythonic. So to understand why I've been talking about these sort of like drawbacks of using Python with Spark, I want to explain the Spark execution model. And this is just sort of one of my favorite things to explain. So I think even if I was giving a talk on, I don't know, decision trees, I might just add this slide for fun. So the Spark execution model goes something like this. Like I said, you create these RDDs, and there's a driver program that's orchestrating all of the work. So this driver program contains a Spark context. And the Spark context is what you describe the operations you're going to do on your RDD. So the driver node, once you say, hey, I have this job, I'm going to submit it, it will look at the code that you've written that operates on a Spark context, and it will decide how to farm out operations to all the worker nodes. The worker nodes have executors. The executors operate on multiple tasks, and the tasks correspond to partitions of your data. So if we were to write a Spark program, it would look something like this. Say, OK, in my Spark context, I want to read in this text file this path with 4 partitions. And see, I cleverly have 4 partitions on the slide. And then I'm going to do something like map over it and create a Pandas series in this case. And a new RDD is created. The same partitions get mapped over. I'm going to filter. I'm going to count it all. And so what is going on is that Spark sees this sequence of operations that you've told it to do. It creates a DAG, a directed acyclic graph of these operations, and it decides, hey, I can actually combine these and do a lot of these simultaneously. And so it has a smart compiler in it, much like a query compiler of SQL. So this becomes more complicated when you begin to describe the operations you want to do on your data frames in terms of Python, right? Because back in this world, all of these blue boxes are Java virtual machines. We don't have any Python processes around here yet. This is when I hate animations. There we go. So when we begin to look at a world in which we're both using Python and Spark together, then we need to start basically gluing Python on the side. So what happens is that we have a JVM that exists on our driver node. We have a Python process that holds the Python Spark context. And so we're going to write very similar code. We'll say like, oh, Spark context dot text file, here's my path. The Python Spark context connects to the Java virtual machine that is doing the heavy lifting in Spark and in PySpark on the driver node through a program called Py4j and using WebSockets. So Py4j allows you to say, OK, here's my fully qualified path name to the class in the JVM that I need to call this function on. So like org.apache.spark.sparkContext, make a new one of those. And so we can control the JVM from Python using this. That's kind of the easy part, right? Because then we need to, we define these operations. There's data out on our cluster. The driver node starts orchestrating the operations that are happening out on the cluster. And the Java executors need to know how to operate on an RDD, and they need to know how to communicate with the Python processes that are actually doing the heavy hard work on the cluster, right? So on the cluster, what Spark decides that it is working with is an RDD, so a resilient distributed data frame, that thing we've been working with, of bytes. So we have a bunch of bytes. And so we need to somehow go from bytes to Python objects. So, well, yeah. So we need to go from bytes to Python objects. And then we also need to be able to move the functions that we've defined in our driver program, for example, toSeries and hasOutlier, these operations that are Python functions that I've defined somewhere else in my code, and then apply them out on our cluster. So there's a few things that happen. First, The functions themselves and their closures, meaning all of the context that you need around a function in order to apply it, gets serialized using pickling essentially, but they use a specialized library called Cloudpickle, so that these can be put into a binary format, shipped off to the worker nodes, and that the Python objects that the toSeries and has outlier is supposed to apply to, those are getting translated from Python to the sort of JVM executor tasks that are associated with them, again, using pickling. So this is a lot of machinery to sort of stick these things together. Essentially, we still have Spark and Scala in the middle, and we kind of glue Python on the side. So really what happens here, and the real trick for when I say like, oh, PySpark is slow, what I mean is that there's a lot of serialization overhead. So there's some serialization overhead in being able to actually write functions that serialize. So there's serialization overhead on the human side, where you need these functions that you write to series and has outlier need to be able to be serialized by the pickling library, but also the overhead of serializing Python objects into bytes, handing those off to the JVM, handing whatever new bytes come back to the Python. Like it's quite a bit of translation and overhead, and it makes PySpark run quite a bit slower. So how does a different execution engine like Ibis or something that has a different execution engine contrast? So an interesting thing here is that, well, I'll get to the interesting thing. So Ibis is a Pythonic API for tabular data. Again, it's just another way to operate on SQL tables while writing Python. So a really, really cool thing about Ibis is that it separates the execution from the API. So the way that Ibis really wants to work is that you describe in a data frame like API what operations you want to do. You want to filter this out. You want to project that. You want to maybe join these two tables together. And what it will generate is SQL that can be executed. And a lot of things know how to execute SQL, right? So there's a few goals of this and reasons why Wes wanted to do this. And one is that it simplifies complex SQL queries. Who here has written a windowing query? I think those are just the worst. It takes me forever to figure out how to do that even half correctly. But being able to write in a Pandas data frame-like style is significantly easier. It also supports some other sort of predefined UDFs, so things like top K. You're like, okay, well, I don't actually want to look at every user and rank them by how much they've spent with my company. I want to look at the top 20 users that have spent the most with my company. Great. A big con here is that this doesn't have UDFs yet. And so UDFs, particularly in distributed systems, depend on what your execution engine you're actually using is. And so Ibis is meant to work with Impala and is first being targeted at Impala. So I'm going to assume like half of you know what Impala is. I'm going to go ahead and explain it a little bit. Impala is an open source, massively parallel query execution engine. It is written in C, and it uses LLVM to be very, very fast at executing queries. LLVM allows them to describe the operations that they need to do, put this into an intermediate representation of the operations that they need to do that's almost akin to like, yeah, you have this many bytes, I'm going to go look over there. And then translate that down even lower to be faster. So LLVM, in this world, and the way that this will surface as being beneficial for Ibis and Impala, or the way this Impala functionality will surface as being beneficial for Ibis, is that the serialization overhead that you get from PySpark and having to sort of stitch together Scala and Python will be eliminated, and everything will just be super fast. But of course, the real drawback right now here is that there's no UDFs. And so you're describing operations that you can do on a cluster, but it amounts to SQL. And maybe simplified SQL, which is nice, but you still don't have UDFs. So it's not that beautiful, wonderful future that you can see doing anything you could possibly do with Python on a cluster. It's still very much just SQL. This is something that they're working on extending, but again, like I said, in order to extend UDS using the Impala system, Wes is actually working on very complicated things having to do with arbitrary execution of Python code, and I do not know what their final design and plans are. Hopefully this will happen in the next 6 months. So, cool thing here about Ibis, which again, also does not have a cute logo, so I found pictures of birds. These are ibises. The way that this works is that you describe the operations that you want to do in your data frame, and in a non-interactive mode, for example, it will sort of buffer these instructions, turn this into a query, a SQL query that can be executed by anything. But in particular, if you've already hooked this up to Impala, it will just work. Wes and the team working on Ibis are very much looking for contributions to different backends. So if you're like, this sounds like a great idea, and I use Redshift, great. Like a Redshift backend would be fantastic. So please come check it out. And that's pretty much what I have to say about distributed data frames and Spark and Ibis and Impala. And I realize this is a sort of broad, large topic, but please ask me questions about anything. Questions? Questions?
So do you think, from your understanding of how the JVM sessions have to communicate with actual spun-up Python interpreters when running UDFs, that performance is slow enough that for a set of jobs it would warrant actually expending resources to bake them into Scala? Or do you think in most cases it would be acceptable for performance issues to write jobs from end to end in Python using the PySpark API for a lot of the actual RDD operations, since UDFs can let us do some additional work in Python?
Sure. So, I mean, cop-out answer, it depends on what your performance restrictions are. I would say in general, without a lot of tuning or thinking about how big your Python objects are, things like that, Python incurs maybe 2 to 3 times performance penalty. And so if that's okay with you and your time frames, that's fine. I think there's trade-offs between the performance that you get of the job running on the computer and the performance that you get from people needing to learn a new language. Luckily, the APIs for both PySpark and Cloudera Spark are very similar. I think the human performance penalty is actually much more around being able to debug these, particularly debugging PySpark. So Cloudera Spark is a distributed system and thus not very easy to debug. You need to go still find all the logs and the things you're looking for. But when you add a Python layer on top of that, and particularly if you add a Python layer on top of that and you're not familiar with Scala or with the JVM, you'll get exceptions and errors that you just don't, like if you haven't familiarized yourself with those yet, like you won't know what they mean, you won't know what's happening there. So I think that there's a few ways that there are performance hits, and I think the more concerning ones are the human side performance hits.
I had a quick question that's quite similar to that. Has there been any research into using Jython to increase the speed of execution by having it just execute natively on the JVM?
Not that I know of.
So one issue with Spark on Scala is sometimes you'll use a third-party library and their data structures don't implement serializable. So you have if you're using Java serialization, then you just run into this problem where you just have to use another data structure. So this is a Python question. Is pickling supported for any arbitrary data type? Or if I pull a third-party library in, might it not support serialization?
Yeah, so, okay. First, a note about Java serialization. Not everything is Java serializable, but you can always specify cryo in your Spark configuration and then use the cryo serializer for that. If you are in the Python world and you are using, and you have the control to use your own data structures, then I highly recommend being very careful and writing tests to make sure that they're pickleable. The library CloudPickle is pretty good at figuring out the full context that's needed and the full closure of a function. If you have an object and it's a well-developed Python library, it should be able to pickle most things. It's not quite the same as oh, this thing doesn't extend to some version of Python serializable. It's usually more of an issue when people run into Python serialization issues, it's usually more of an issue of just trying to serialize something that's fundamentally unserializable, not a normal Python object. Python tends to be made out of very simple things. You have lists, you have dicts, it's simple and straightforward. People sometimes will try to serialize database connections. You're like, well, you can't serialize a database connection. There's a way to get around that, but it's not possible. So I don't think I really answered your question still. I did? Good. Good.
Actually, I have a question here. So does this actually mean that we have scope to use other programming languages to create a PySpark-like API instead of using Python, since we can serialize it to Java-specific objects?
I'm not sure I understood your question. Is your question that
So
we should be using other languages, or?
So can we actually create PySpark-like APIs instead of, so PySpark uses Python as the base language, so instead of that, if we use some other programming language, and since it's going to serialize it into Java objects and run on a JVM?
You mean can you use other languages to build something like that? Yeah. So you would need, you can, it would be incredibly custom still. So Spark has added support for R, Spark R, and they do something similar where there's a library where you can control objects in the JVM like a Spark context object from R. But even there, they haven't implemented UDF. Well, let me rephrase this. They had UDFs in. It was done in a very non-maintainable inside of the software kind of way, and so they removed it before they added it back. They added Spark R to Spark. It used to be a separate project. And they're working on adding that back in, but the translation of UDFs, like R UDFs, between something that's written on a local machine and something gets shipped off to a cluster is still really difficult. And so as long as you have some way to start up a JVM, communicate with that JVM, and operate on objects in it, then you can create a different language wrapper for Spark if you want. Like a Juliet one, that would be cool.
Thanks.
Other questions? Sweet. Well, thanks for humoring me when I didn't talk about Sparkling Pandas.